Hello everybody. Yeah, I'm back and you're back as well, ready for round two, as somebody just said in the chat. So in the stream tonight, I'm going to be going through a full work through of this paper here, which is the PMT Education predicted paper. I say predicted, it's basically a set of good practice questions, not necessarily what will come up in the exam, but it's a good set of questions to look through all the topics that might come up. And this one is based on OCR. So anybody joining the stream, I have put it in the chat as well, but this is kind of the topics which are going to come up in the OCR Exploring Physics paper. But of course, a lot of these kind of topics also come up for Edexcel, AQA and other exam boards as well. So yeah, and I'm going to be doing, good question, says RS, I'm going to be doing a live for the AQA paper tomorrow. So tomorrow night, Tuesday night, and obviously this will also be available afterwards to re-watch on YouTube, I'll be doing the PMT AQA paper, so I'll be going through all of the questions for that as well. So what I'm going to be doing is having a go at all of these questions. I haven't actually worked through them myself before. So I'm just going to, I guess, kind of go through my approach to how I do each of these questions. The big plan is to try and do the whole thing during the stream tonight. But also, it says down here, it does say that I'm going to be doing some Paper 2 revision masterclasses. I've got one coming up on Wednesday, which I think is AQA. Actually, it says it on the main page of my website. So if you head over to A-Level Physics Online, it does say here what's coming up, so you can click load more and then it comes up with the things I'm doing. So I'm going to be doing an AQA class on, is that right? Hold on, let me just check. View all the masterclasses here. So I've got basically this week, I've got on the Wednesday, I've got AQA paper 2. On Thursday, I've got Edexcel paper 2. Then on Saturday, I've got OCR paper 2. Sunday, I'm going to be doing AQA paper 2. And then the next weekend, after you've all done your paper 2 exams, I'm also going to be doing an AQA paper 3A masterclass. So I've got that there for the Sunday. I'm not quite sure why it has those dates, but let me just refresh that. Anyway, those dates will all kind of get updated and so on. Yeah, so basically, I'm going to be doing some of these masterclasses. You're obviously all welcome to join. If you want to come in, they're a 2-hour-long session and you can book a place on the website. Okay, so let's have a go at some of these questions. What am I doing? I've got a beard just because I haven't really shaved over half term. That's all it is. I just couldn't be bothered to have a shave every day. So yeah, since I haven't been doing as many live streams, as many masterclasses, I've just grown a bit of like a stubbly beard, but that will be going soon, don't worry. Right, so here we go, 2 hours, 15 minutes. So I suspect that's about how long the live stream is going to be today. Which of the following shows the correct base unit for the volt? So my approach would be for a question like this, when we're looking at base units for something like the volt, now you might just remember it, which would be the best way of doing things. I'd say probably, if you're not sure, maybe just look at what we've got over here. So we know that W equals VQ. So V is going to be the energy transferred per unit charge. So then I've got to think about what equation could I use for energy? Well, let's just think of any equation that we could use to work out energy. Maybe the energy is equal to a half mv squared if we're thinking about kinetic energy. So that's effectively a half mv squared. So that's an equation that we can use for energy. And charge is going to be current multiplied by time. So now I've got, again, a couple more equations. I can think about what units might be useful. So if we've got mass, that's kilograms. If we've got velocity, that's meters per second, but that's all going to be squared. And then we're dividing that by the current, which is in amps, times time in seconds. So that all looks a bit messy, but effectively we've got a kilogram, and then we've got meters squared, and then we've got seconds to the minus 1 squared, so that's seconds to the minus 2. Then we're going to be dividing by amps, so that's going to be amps to the minus 1. And then we've got seconds to the minus 1, which I guess would add on to that. So we would have kilograms, meters squared, second to the minus 3, amp to the minus 1. So if you can't remember the base unit for the volt, that would be one approach. It doesn't matter which order these go in, but looking at this and then looking at the options, I can see that C happens to be the correct answer. So here my answer is C. Is that correct? Let's see what other people are saying. Yes, it does appear to be correct from the mark scheme I've got here. And yeah, basically, if you want to kind of add your answers in the chat, that'd be amazing to see. Yeah, people are saying the beard looks good on me. Well, we'll see. Right. Yeah, if you want to put your answers in, please do so. Right, the next one, we've got a question about the percentage difference between the student's value and the accepted value. So this one here often comes up when we're looking at the acceleration due to freefall. So basically, that's the true value, the accepted value, and their experimental value is 8.75. So my approach would be looking at the difference between these two things. So I'm going to have a look at the experimental value, take away the accepted value, divided by the accepted value, and then we're going to multiply that by 100. So 8.75 minus 9.81 divided by 9.81 times 100 is equal to, well, it says minus 10.8, but really it's the modulus of this. We just want to know the positive value, the change in these two numbers, and that's equal to minus 10.8. So my approach would be to work out the number and then go back to look at what this could be, and then when we do that, the answer that's closest is going to be A. So here my answer is A, which is what quite a few people have said. We've got Ashraf, we've got Kim. Yeah, that's it. People are saying the right things. This is good. AG2 San, very good. If you did this yourself, you do your own value minus the true value. Yeah, that's kind of what I did. I just did my own value minus the true value divided by the true value. Which of the following particles is the antiparticle of the electron? So you've got electrons, which are matter, and then we've got anti-electrons, the positrons, which are antimatter. Now it can be represented like this, but of course an electron can also be represented as beta minus, and therefore the antimatter equivalent is the beta plus. So this one here, the right answer in this case is C. Okay. Right, is this only for OCR? No, now this question here, this is not just an OCR question. This question, what is the antiparticle of the electron? That is a question that anybody doing OCR, EdXL, EduCast, WJC, all of you should know that. So even though these are OCR style questions, the content is just A-level physics. Right, the current in a resistor is 20 milliamps. How many electrons pass through the resistor in 4 minutes? So I'd be thinking about, to look at the number of electrons, we want to maybe think about the charge transferred, where Q is equal to IT. But also this charge is going to be equal to the number of electrons times the elementary charge on each. So that is an equation given to you. This is an equation they don't give you, but I think this is super important. Okay, so Q equals NE. The total charge is the number of things times the charge on each thing. So if I put the two things together, we can say that NE is equal to IT, and therefore the number is equal to the current times the time divided by the elementary charge, which is going to be 20 times 10 to the minus 3 times 4 times 60 for the time in seconds, divided by 1.60 times 10 to the minus 19. So that would be my approach. So these two equations I'm going to put together. People are saying C. Right, let's see what we've got. So we've got 20 times 10 to the minus 3 times 4 times 60. 3 times 10 to the 19. 3.0 times 10 to the 19. So it's going to be a big number. And therefore the closest one is this one over here. The answer is C, which is what loads of people got. Jack, Ashraf, AG2 San, loads of people getting C. Good stuff. Right, the next one. A carbon-12 atom loses an electron. So it's now going to be a carbon-12 ion. It's accelerated to a speed of 350 meters per second. It enters a magnetic field of flux density 50 millitesla. What will be the radius of its path? Now, in the actual data sheet, you don't get given the equation for the radius of its path, but it's one of the things that comes up quite a lot. Now, if you're not sure, you can basically say that the force on that particle is going to be BQV, and that force is also going to be equal to mv squared over r. Okay, so this is the force due to the magnetic field, which causes this centripetal force on that charged particle. And if we equate the two things together, we can say that BQV is equal to mv squared over r. One of the v's cancels, and therefore we can say that BQ is equal to mv over r, or the radius is equal to mv over BQ. So now we just need to look at the mass of this particle, which I guess we can work out. So if it's a carbon-12 atom, the mass is going to be equal to 12 times the atomic mass unit. So effectively we're going to say there's 12 things in it that kind of make it up. Effectively the mass of the electrons is going to be negligible. So the mass of it would be the atomic mass unit. So that's 1.661 times 10 to the minus 27. The velocity is only 350, so that's a really low velocity for a particle. Normally we have stuff in a range of 10 to the 5, 10 to the 6 meters per second. Going to divide that by 50 times 10 to the minus 3, because it's a millitesla. And then we're going to multiply that by the charge, because it loses an electron, so it will have a charge of plus 1.60 times 10 to the minus 19 coulombs. So this thing here is the mass of that, and we're just going to assume the mass of this carbon-12 ion is just going to be 12 times the mass of a nucleon. So people are saying A. The answers all look pretty close, to be honest. So let's see. The hardest bit is doing maths while talking. (8.72 times 10 to the minus 4). So this was 8.72 times 10 to the minus 4. And therefore the answer is this one over here, which, to be honest, A. Jack, yes, asking, is this stream useful for AQA? Yes, it is, because you could potentially be asked a question similar to this in an AQA paper. Yeah. The slow-mo, yes, I do remember you. Actually, it's strange. I also kind of recognise your name, the slow-mo, with the red kind of icon dot next to your name. So yeah, this is for all examples. This is useful for everybody. I would say that if you've got something which is moving with a radius of about 1 millimetre, that's kind of that, which seems quite a small kind of circle it's going to be going through. I suspect it's really because they've given a speed which is too low. Normally, if that would be, you know, maybe 100 times bigger, we then maybe get a radius of maybe 10 centimetres, for example. So yeah, that would be my approach. I got that number, and therefore that's the appropriate answer for this. Right. Actually, this is going all right. This is going all right. Right, number 6. Okay, people, what do you think? Is it A, B, C, or D? So this is about the spontaneous nature of radioactive decay. So two things about radioactive decay. It's going to be spontaneous, and it's also going to be random. Okay, and I think a lot of you might have done this question before. Yeah. So the random nature, I guess, tells you that it's not really possible to predict when it's actually going to happen. But I think the fact it's spontaneous means it just occurs, and there's nothing you can do to stop it or to speed that up. And so I think that it's not possible to predict when a particular nucleus will decay is because it's random. It's not possible to predict whether that is emitted. Well, that's just not true. That's kind of irrelevant. So I think the correct answer is B. So who's got the right answer? Jack says B. AG2 Sam says B. The slow-mo says B. David, yes, B is the right answer. A is a true statement, but it's a true statement that doesn't answer this question. So I think that B is a true statement that answers this fact, the fact it's spontaneous, The spontaneous nature means that it can decay on its own without any external influence or intervention. So basically you can't heat it up, pressurize it, pray for it to kind of emit another particle. It's just going to do it whenever it's ready. Okay, a space heater transfers 1500 joules of heat, energy I guess, to a room per second. If the PD is 230 volts, what is the resistance? So we've got, it says 1,500 joules per second, so I guess that's really the power. We've been given the potential difference and we want to work out R, and therefore we could say that P is equal to V squared over R. So R is equal to V squared over P. So just using one of the many equations for power. Don't forget, of course, that P is equal to VI, P is equal to I squared R, P is equal to the energy per unit time, power is equal to the work done per unit time, and power is equal to force times velocity. So just a few of the other equations that we can use to look at power. But now we're going to look at it in terms of resistance and potential difference. So that's equal to 15,000 squared over the power, which is 1500 joules per second. So that's 1500 watts. No, sorry, 230 squared, isn't it? Okay, people are about to say that. Okay, hello Perks, nice to see you. You enjoy learning physics. Yes, you can enjoy learning physics no matter what age you are. Okay, so let's see, 230 squared divided by 1500 is equal to 35.27 ohms, and therefore the closest answer I can see is going to be B. So my answer for 7 is B. There we go. Okay, okay, right, so yes, Miles, this is OCR. Have I got something to drink to keep me going? Yeah, basically I had a litre of, 900 millilitres of Lucozade about half an hour ago, therefore buzzing. Not a good thing to do for the rest of you if you're revising and you're going to go to bed, but basically had a load of Lucozade and now I've just got a load of water to keep me going, because to be honest, talking for a couple of hours, it does kind of get to your throat after a while. Okay, right, so what is a resistivity? So I would start by saying that resistivity is equal to RA over L. So that'd be my first approach. But we've been given the length as X. So that means resistivity is RA over X. But we haven't been given R, but we know that R is equal to V over I. And if we put this into there, the resistivity is equal to VA over IX would be my approach. Is that one of these? VA over IX. Yes, so my answer for 8 is D, because that one there is this one over here. So that one there, that was an okay question actually, I thought. Right, D. Okay, Ashraf says that, yeah, cool, thank you so much. Right, number 9. Okay, 2 electrons are separated by a distance of 2 times 10. So here are my electrons, and the distance between them, R, is equal, here we go, so I've just drawn a diagram. The distance between their centres is, say, 2.0 times 10 to the minus 10 metres. An estimate of the gravitational attractive force over the electric repulsive force for these 2 electrons. So, in order to do that, we know that F, gravitational, is equal to GMM over R squared. So that's my gravitational force, which is going to be repulsive. So I just put in a negative symbol there. There's also going to be, I'll do it in this colour here, a force due to the electric field. And I'm going to say that's equal to, that's going to be equal to QQ over 4 pi epsilon naught R squared. Is that right? I think so. And therefore, if I want to look at the size of that divided by the size of that, that's basically equal to this divided by that. but we've got an r squared, so we've got a 1 over r squared divided by 1 over r squared, so they'd cancel, and therefore that's equal to 4 pi epsilon naught times g m m over q q. I think that's right, isn't it? Yeah, so the answer here doesn't depend on r. Yeah, so basically the gravitational force is going to be gmm over r squared. The electrostatic repulsion is going to be qq over 4 pi epsilon naught r squared. So I think that the r's cancel, and therefore it's just this. So that's going to be equal to 4 times pi times epsilon naught, 8.85 times 10 to the minus 12 times big G, which is 6.67 by 10 to the minus 11. Let me just check that. 10 to the minus 11 times the mass of them. So if it's an electron, then the mass is going to be 9.11 times 10 to the minus 31, and that's going to be squared. And then we're going to divide all of this by the charge on them, which is 1.60 times 10 to the minus 19 squared. So basically, I think this is just a massive test of my memory of if I can get all these constants correct. So let me just start working this out. Is that right, everybody? Okay, so let's have a look. So I should have squared that. I've got 2.4 times 10 to the minus 43. So 2.40 times 10 to the minus 43. So that means I think for here, my answer, something in the order of 10 to the minus 43, the correct answer is D. Okay, and basically, this just shows that the gravitational force is much, much, much smaller than the electrostatic force between things. So it's D. Anyone else getting D? Yeah, so good. Yeah, so Jonathan, Ashraf, AG2, yeah, all that good stuff, getting the answer of D. So this one here, it's one of those questions where if you get a question like this in the exam, you can do it because there's nothing here that you can't do, but it just takes a long time to actually work out what's going on. So I just drew a quick diagram. I wrote down the equation, I kind of realised what cancels, and then it just takes a long time to actually put it in your calculator and get the answer. So this is the kind of question that you could see and go, I know how to do that, but I don't have time now. So you could skip it and move on. And you might just recall actually that this is kind of a number that you might have worked out maybe in a question in class or by doing one of my daily workout books. But 10 to the minus 43 is kind of the order of magnitude. Okay. A standing wave is set up on a string. If the frequency of the fifth harmonic is 150 Hertz, what is the frequency of the third harmonic? Okay, so my first thing is I'm just going to draw the wave. And if you've got the fifth harmonic, you'd have a node at the end, and you'd have more nodes there. So the wave would look like this, wouldn't it? So this is going to be the fifth harmonic. Okay, and that's when the frequency is 150 Hertz. And of course, if we now have the third harmonic, we'd have a couple of nodes and we'd basically have the wave look like this. I've drawn a lot of waves recently for standing waves on a string. Okay, what we don't know is the frequency, but what we can see is the wavelength has increased. Now, of course, we know that the wave speed is equal to f lambda. And what we can see here is that as we've gone to a longer wavelength, this has got bigger, so that means the frequency must decrease in size. And so the wavelength now is going to be, well, if that's 150 Hertz, I guess it would be, I just need to work this out. I guess it's 3/5 of 150. Yeah, that's right. Who said that? David, thank you. Yeah, so basically now the frequency is going to be 3/5 of this because that's now 5/3 of that length. So it's 3/5 of 150. and that's going to be 150 divided by 5 is 30 times 3, which is going to be 90. So here the answer is going to be 90 hertz, and therefore the answer is C. Is that right? Yes, it is. Phew, thank you. Good, yeah, good. We're doing all right, aren't we? Okay. A ray of light passes from glass with refractive index 1.5 into the air. So here's my glass, where n is equal to 1.50, and it says the ray of light passes from the glass into the air. So I'm just going to do my sketch diagram like this. So here's my normal, that's the ray of light, and I guess as it goes into the air it's going to speed up, so it's going to move away from the normal. So it says here it passes from glass into the air. If the angle of incidence is 51 degrees, so this is 51, which of these is true? So let's have a look. Right, in the chat, people are saying it's B. It internally reflects off the glass air boundary. Only D makes sense. The glass refracts towards the normal in air, so that can't be true because it would have to refract away from the normal, so it can't be D. And it's definitely not that one. It doesn't go without any change in direction, so it can't be A. So neither of these can be the answer to the question. So it says that it passes from the glass into the air, but both of these are either when it moves along the boundary or it internally reflects. So in that case, let's have a look at the critical angle. And basically we can say that sine of the critical angle is equal to 1 over n, which in this case means that the critical angle must be sine to the minus 1 of 1 over 1.50. So let's just work this out. Oh, hold on. If I set this up to radians, let me just set up. Okay. Always make sure you've got your calculator set up properly. .8. Okay, so the critical angle is equal to 41.8, and therefore that's bigger than the critical angle. And therefore it's going to be totally internally reflected, so it would come off at an angle like this. So for this then, the light reflects at the glass air boundary, so B is the correct answer. Although I don't think that, this is B, but I think that was not a great question because of the way it's phrased. Because it says the ray of light passes from glass into air, that means it's like saying the light has passed from glass into air. It should have said that a ray of light approaches a boundary with an angle of 51 degrees. But there we go. So this is my approach. Draw a diagram, use a pencil and a ruler. And don't forget, people, your protractors. I've said this every single live stream, every single masterclass. Bring your protractors. I worked out the critical angle from the refractive index, and therefore we can work out what actually happens to it. Okay. Right, a metal aircraft travels at 100 meters per second, so that's the velocity. The vertical component of the Earth's magnetic flux density is 2 times 10 to the minus 7 Tesla. What's EMF induced across its wings if the length measured tip to tip is 45 meters? So, basically this is like the aeroplane. I'm going to draw a rubbish picture of an aeroplane. Okay, so here's an aeroplane. Okay, does that make sense? And then the aeroplane is going to be flying above the ground, but you've got the field lines kind of from that field sort of going into the ground. And so as it's going along, we've got a certain length of a conductor, so from here to here, cutting field lines as it's moving along that way. Right, okay. So we've got B, we've got L, and we've got V. Okay, help me out, people. How would you approach this question? Let me just have a look in here to see what they say. What equation would you use for this one here? So we need to find V. We need to find big V, sorry. And we've been given the velocity, we've been given the length, and we've been given this. So what equation would you use? This one here doesn't seem to jump out as a normal standard A-level question. Of course, we could work out, I don't know, what could we work out? Equals BLV. Yeah, so I think there's equations to do with force is equal to BQV, or the force is equal to BIL. So that would give us the force. But we want to know the induced EMF. So EMF is going to be equal to N phi over delta T. So the EMF would be equal to the flux, the rate of change of flux, okay, I guess my approach would be, so my approach then would be, so this is thinking, but this is not like a nice question I've really seen before. The flux is going to be equal to the magnetic flux density times the area, and effectively, if it's moving 100 meters, so let's imagine looking down on the plane, the area here, in 1 second, the area swept out by the wings is going to be equal to the length, which is going to be 100 meters, times this dimension of 45 meters. So basically the area per second, so the area per unit time, is going to be equal to the velocity of that plane times the length, because the velocity is equal to the distance travelled per unit time. So this means the area per unit time is going to be equal to the distance travelled times the length over the time. And if we're now looking at the area per unit time and we multiply that by the magnetic field strength, we'll then get the flux per unit time. And therefore the flux per unit time, which is equal to the EMF, is going to be equal to BA over T, which is equal to BVL. So that's going to be the EMF. It's going to be BLV. So I would say then, and again, if you're ever not sure, just multiply all the numbers together. So the magnetic field strength is 2 times 10 to the minus 7. We're going to multiply that by the velocity, which is 100 meters per second, times the length or the width that's sweeping that area out, which is 45, which is 9 times 10 to the minus 4, which is going to be 900 times 10 to the minus 6, and therefore the answer for this is D. Okay, that would be my approach. Does that make sense? You don't need the number of turns in this case because it's going to be like one thing. It's like one piece of wire moving through the field. So effectively N is going to be 0. I apologise for my messy nature of this. That's just the alpha scattering experiment, in which alpha particles are shot at a gold foil, can be used to determine an estimate of the radius of the nucleus. Which of the following are true? Alpha particles are helium atoms. That's not true because they're helium nuclei. So 1 isn't true, which actually means it can't be A or B or D. So because 1 isn't true, the only correct answer for this must be C. And let's just check that. Most alpha particles do pass straight through the gold foil. Yes, they do. Have I gone? Was there something wrong at my end with stuff? Okay, let's have a look. CPU usage 6.8, 6.3. That looks all right. Okay. Did I just disappear for a second? Sorry about that. I'm back. Very few alpha particles are deflected through angles greater than 90. That's true as well. So 2 and 3 are correct, and therefore C must be the correct answer. Okay, a step-down transformer has an input PD of 250, so that's going to be V primary. There are 200 turns on the primary coil, so that's going to be N primary. 50 turns on the secondary, so that's N secondary. And it's 80% efficient. What is the output voltage? So what is VS? So this one here, every time you get to a question like this, just be very clear about a lot of the numbers. So what is the output voltage? Well, if we ideal one would be equal to the primary potential difference, that's 250 multiplied by 50 over 200. So that's basically a quarter of 250, which is going to be 62.5. Okay, so that would be the ideal is equal to 62.5 volts, but we're just going to look at 80% of that, so 0.8 times 62.5 is equal to d volts. So here my answer for this is going to be A. Is that the right answer? Yes, there we go. That answer looks all right, doesn't it? By the way, if there's anything I don't make sense on, you can always go back and rewatch that part of the video. Which statement is true about safely maintaining a chain reaction in a nuclear reactor? So water can be a moderator, that's true. And that means it moderates the speed of the neutrons so that we do get fission, and it can be used as a coolant. So that is a true statement. The purpose of the control rods is to ensure neutrons released from fission are slowed down. No, that's not what a control rod does. That's what a moderator does, so that's not true. We're not releasing radioactive waste products into the coolant material because those radioactive waste products tend to stay within the spent fuel rods, so that's not true either. And they're not always fully down, they're often up, they can move up and down depending on how quickly that reaction wants to go. So here the answer for 15 is A. There we go. Right. Is there some issue where things are lagging at the moment? I'm just looking at other things. Everything seems to be working as normal. It's like 8,000 kilobytes per second. There's some other numbers I don't know what they mean. CPU usage is at 8%. Is that a bit high? Okay, I think it's just there's so many people watching this who are kind of getting ready for their exams coming up. By the way, if you haven't already done so, have a look at my masterclasses. You can book them by going to A-level physics. Where is it? It says over there. If you look down here, it says go to alevelphysicsonline.com. If you go to my website, you can book a masterclass. I'll be doing 2-hour-long sessions. These are going to be Wednesday, Thursday evening at 7 o'clock, and then Saturday and Sunday morning from 10 o'clock until 12 o'clock. So there we go. Right. Okay. Right, let's have a look at this question then. So, we've only done 15 marks on the whole paper, and we're already 40 minutes into this. Let me just get a drink. How's everybody feeling for their exams, by the way? Is everybody watching this an OCR student? Or are you just watching some general physics kind of questions that could be relevant for you if you're AQA, EdXL, OCRB? Be great to know in the chat who is doing what in terms of their exams. Okay, we've got AQA people here. Hello, 22 Blue. We've got OCR. We've got AQA, general knowledge, yes, OCR, AQA. I'll be doing an AQA paper tomorrow. I'll be working through the PMT predicted AQA paper. But of course, I think you'll see that this is the same physics. It's just sometimes there are different, it's the same physics, just different exam boards test different things in different papers. Okay. Right. Okay, so we're doing all right, aren't we? Explain the purpose of the coloured filter. So this is the original Thomas Young 1800 experiment, so they didn't have lasers at the time. So you've got effectively a continuous spectrum given out by the light. We then go through a colour filter. And I guess what's happening is that the colour filter is only going to let one colour and therefore one wavelength of light through. So when it goes through the single slit, there's only going to be one wavelength which is going to be diffracting through that. And then we have coherent light that diffracts from the two slits side by side. And then of course we have our sort of constructive and destructive interference over here. So explain the purpose of the colour filter is to ensure all the light has the same wavelength as it passes through the single slit, would be my approach. I don't know if that's really 2 marks. They've got the colour absorbs all the wavelengths except one. I guess, yeah. Ensure all the light has the same wavelength as it passes through the single slit, as it will be monochromatic. So that's the purpose, is to make sure that we have this monochromatic light. Yeah, that's why we have that colour filter, so that would be my answer for that. Have I spelt the word wrong? Have I? Monochromatic? How have I spelt it? Mono. I think I spelt it right, it just looks a bit rubbish. By the way, that is a good point, well raised, is that make sure you do keep your spelling as neat as you possibly can. In modern day experiments, a laser is used to replace a candle. What property of laser light allows the experiment to succeed? So the property of laser light, I don't know if that's the right phrasing, but the property of laser light is that it is coherent. And basically, if you've got coherent light, when you send one laser beam through the two slits, but the laser light that's coming through will be coherent, so it'll have the same wavelength, a constant phase difference, it'll have the same frequency and a similar amplitude. Okay, right. So there we go. That one looked okay to begin with. Describe how a student could measure the fringe width of the bright fringes that would form on a screen behind the double slit. So you can measure the fringe width with a ruler over at least 10 fringe spacings. So basically that's the method. Measure the width of at least 10 fringes, use a ruler or vernier caliper, divide the measurement by 10. Yeah, so a ruler over at least 10 fringe spacings, then divide by 10. Okay, a dark fringe is observed at point X. Label the distance, label clearly on figure 16.1. Okay. The distance is equal to the path difference between the rays of light from the two slits to point X. Right, I think I've just drawn over it here, but if this is the distance, say that's going to be a distance of x1, and this is x2, then x2 minus x1 is going to be equal to the path difference, equal to half a wavelength. So that's equal to some multiple, so I guess it's n plus a half multiple of the wavelength, which I guess would be kind of like, I guess that distance and that distance are the same. So I guess it's going to be this distance in here where we have that. So I think that a real exam wouldn't ask you to label something that small, but it's basically this red line here. We can see that there's now the same path difference from this point to this point to the screen, but this difference here is going to be equal to a path difference, which is equal to half a wavelength, which is why we get the maximum destructive interference in the dark fringe. Okay. Right. Sorry, I'm just going to ban somebody from, just going to hide user on the channel. Right, the next one then, we've done that. Explain how the path difference determines the light intensity as X is a minimum. Explain how the path difference determines, causes the light intensity to be a minimum. Basically, we will have, sorry, by the way, I'm trying to kind of, because it's just me doing the stream tonight, I don't have anybody moderation, but basically if you say anything that's like bad, I'll just ban you from the channel forever. That's like the easiest way of doing things. Okay, so this one here, 3 marks, think about bullet points. Basically we have maximum destructive interference as path difference is equal to half a wavelength. What else do I need to say? As path difference is equal to half the wavelength, so the phase difference is pi radians, or effectively they're in antiphase. Cool. Yeah, that's it, I think, basically. Yeah, so you've got one wave that's like this, the other wave is like that, and effectively you've got the superposition of these two waves, and as they interfere, the peak and the trough kind of cancel each other out, giving you basically no wave at all, so that's why it appears to be dark. So questions like this, writing bullet points, diagrams could help as well. Okay, what is the role that diffraction plays in producing the interference pattern that will be seen on the screen? So diffraction is the fact that the light spreads out as it moves through the gap, and therefore we've got the waves kind of crossing over each other. So I guess diffraction causes the waves to spread out. So that means, so they superpose. Did I miss a question, did I? F. No, this is, I think this is right. Diffraction causes the waves to spread out, so they superpose and interfere. Something like that, isn't it? And they interfere, I guess, on the screen. Okay. A student conducts a similar experiment and feels that the fringe width is too small. Make 2 suggestions on how the student could adjust the experiment to increase the fringe spacing. So here, what I'd be doing is I'd be looking at this. I'd find an appropriate equation. So here we know that lambda is equal to AX over D. And basically we want to have the value of X to be bigger. So basically if we've got the same fixed value of wavelength, we either need to increase the separation between the slits, or we need to, we need to, if we want to make x bigger, then x is equal to lambda d over a. So basically, if we've got something, we can either increase the value of d or we can decrease the value of a, or I guess we could have a different wavelength, but that's not necessarily something that's easy to control. So I'd say that you increase the distance to the screen. So imagine if you had the screen twice as far away, the fringe spacing would be twice as big. So increase the distance to the screen, or you could decrease the slit separation. So there are two ways that you could do that. Okay. Right. Yeah, what's the difference between A and X? I always forget, but basically A is the distance between the slits, X is the fringe separation, unless you are an AQA student where they use a similar equation that says lambda is equal to WS over D. So if you are, this is basically the OCR equation. If you are an AQA student, you'll have seen this equation, which is basically the same thing, but AQA used W for the fringe spacing and S for the slit separation. Okay, but yeah, they could be either really. Right, number 17. Only a few more questions left. We're going to be here forever, aren't we? Okay, hopefully this is all good though. But again, if you're watching this afterwards, you can just skip forward to the question you need to. An ultrasound is to be taken of a patient's organs. They have the following data. So you've got speeds of sound and air in the tissue and the density. Calculate the acoustic impedance of air and of the tissue, providing appropriate units. So the equation we need is that Z is equal to rho C, where Z is the acoustic impedance. This, by the way, is an OCR specific question. So if you're doing AQA, don't panic unless you've done the medical option. So if we want to look at this, we can just look at the density of the material. So let's do air first of all. That's going to be the density of air. So 1.3 times the speed of sound in the air, 330. And that's going to be 429. So for air, I'm going to say 430. And of course the units, if you're not sure, if you can't remember, which is something that you probably wouldn't remember. Okay, so that's going to be meters per second times kilogram meters to the -3. So that would be kilogram meters to the -2 second to the -1. So that'd be kilograms meters to the -2 second to the -1. I don't think it really matters about the order, but I think that looks quite nice. I'm just going to check that answer. Yeah, that's good. And then of course if we're looking at the tissue, that's going to be equal to the density, which is 1100 times the speed, 1540, which is equal to 1694000. So I'm going to say that's, I suppose they've given their data to 4 significant figures up here. That's to 2, that's kind of to 4 strictly speaking. So I could give that as 1.694 times 10 to the 6. And again, the units would be kilogram meters to the -2 second to the -1. Somebody getting affected by adverts, that's not me, that is just YouTube doing its thing, earning a bit of money for me, but not much. But yeah, if adverts happen, yeah. I think that's kind of strictly speaking what the right answer should be, because that's to 4 significant figures, and so's that, although that makes me uncomfortable because I know they just mean that's really to 2. It's not 2 significant figures because the zeros, a trailing 0 adds to the significance of that data if you look at the way that they do it and stuff. Okay, right. Show that the ratio of the reflected intensity to the incident intensity is approximately 1. So this is going to be using, I think, the biggest complicated equation from A-level physics. So I'm going to write it out. It's in the data book. that says IR, the reflected intensity over the original intensity, is equal to Z2 minus Z1 squared divided by Z2 plus Z1 squared. Now, I guess we don't even really need to do this, because basically we've got something like 2 million effectively. So you've got 2 million minus 400 squared over 2 million plus 400 squared, which is effectively 2 million over 2 million. So effectively, because Z2 is much bigger, much bigger than Z1, effectively in this, Z2 minus Z1 is approximately equal to Z2, and Z2 plus Z1 is approximately equal to Z2, and therefore this thing here just becomes Z2 squared over Z2 squared, which is just going to be equal to 1.00, I guess. So I guess you probably should be putting in the numbers, but effectively what we've got is where one of the numbers is so much more bigger than the other one, then this number and this number are going to be pretty much the same, and therefore that divided by that is just going to be equal to 1. If I was going to do this in the exam, I probably would put the numbers in, so I'd just actually do, well, whatever that is, which is whatever it is. I guess if we look at that answer and we take away 430 is basically 1693570 squared divided by 1694430 squared, which if we do that is basically 0.9989, which is approximately equal to 1. Okay, so that would be the approach I take in the exam, but basically, yeah, that's what I'd say. Yeah, by the way, this is an equation for acoustic impedance. It looks complicated, but in a way, because it's quite a complicated equation, and there's only one of them, they tend to use it in isolation, so it's often the case of just putting numbers in. But this is just an OCR thing, which you don't need to know about if you're just doing the normal Edexcel or normal AQA paper. Right. The trainee sonographer gets a poor image, then they realise they forgot to put gel. So if this is a transducer for sending out the kind of ultrasound signal, and this is the tissue of the person, if there's an air gap in the middle, what this means is that all of the signal that comes out is reflected at the boundary and it reflects back again, which is what we found out in that previous part of the question. So if we're going from something like air into a tissue where the two numbers are very different, that's when we get a lot of reflected signal back again. If the numbers are closer, imagine Z2 was approximately equal to Z1, then that means Z2 minus Z1 would be equal to 0. And then you'd have 0 squared over whatever number that might be, and that's just going to be equal to 0. So if you had the two numbers being very similar, then all of this would become 0, and that means the intensity of the reflected radiation, the reflected ultrasound, is going to be pretty much 0. So nothing's reflected, and all of that signal gets through. Okay, is that all good? Right. How are we doing? Am I here? Am I here, or is it lagging again a bit for some reason? Right. Okay, so basically what you need to have is you put the gel, you impedance match the gel to this thing here, and that means when you've got the gel there, the thing is going to go through. So basically gel has an acoustic impedance approximately equal to the acoustic impedance of the tissue, and therefore very little ultrasound is reflected at the boundary. And I'm sure if you're doing this, you'd add a few more bits of stuff. Okay, right. We then have something about an A scan. So an A scan, which I'm not going to do the full kind of written explanation, but basically this is kind of the graph that you get for an A scan. You'd have your initial signal, and then a short time later you might pick up other smaller signals as a wave that goes out, is reflected from a boundary or a change in medium, and then it comes back again. And of course, if you've got the time along the bottom and you know the speed of that wave, you can work out the distance travelled, because we know that the speed is equal to the distance travelled divided by time. So that means the distance is going to be equal to the wave speed times the time, but that's going to be the distance out to something and back again, and therefore the distance is actually going to be half of this amount. Okay, so this is the time to go out and come back again, so the distance to that object S is going to be equal to half that time between the signals. Okay, so there we go. How does it work? The transducer sends out a signal, and then it then detects the echo that it receives. And I guess you might talk about the fact there's a piezoelectric which is changing its shape when you've got an EMF applied across it, and then when that changes shape it then induces an EMF that we can measure. Okay, I'm not going to go on to that a bit more. Explain how the results from the A scan can be used to find the size of a particular organ. I guess if you had a cross section of a body, so here's like the body, if you sent out a signal, some of it would reflect off this side of it, some of it would travel through and then reflect off that side, and then you might get the scan that basically looks like this. And if you know the time between these two peaks and you know the velocity, then the distance from this bit to this bit is going to be equal to that wave speed times half the time between those signals. Hopefully that helps. And this is an OCR question, but a lot of the other ones are suitable for AQA people as well. Okay, the next question then is about a microwave, 35 centimetres width. A bar of chocolate is placed in the centre and it's turned on. The chocolate melts at distinct points. Describe the formation of stationary waves in the microwave oven. So this one is just a standard question about how a stationary wave is formed. And basically what you have is you have a wave that's moving in one direction. That's then going to reflect off a boundary. In this case it might be the other edge of the microwave. And then we then have a reflected wave coming back in the other direction. Now, because that one and that one have the same wavelength, they've got the same frequency, and there's this constant phase difference, the two waves are going to be coherent, and that means we're going to have points where we have constructive and destructive interference. And what this then does is, between the inside surface of that, it's going to set up a series of points where you have maximum constructive interference, which are the antinodes, and maximum destructive interference, the nodes. And these are going to be going all the way along through that. If it's a microwave as well, you know that normally the wavelength is in the order of about 3 centimetres. And that means it might be a couple of centimetres between the antinodes, the kind of the melted spots on here. Okay, so we're going to have antinodes and nodes that we have kind of through this. So, describe the formation of the stationary waves. I guess, again, I'm not going to write out the full thing. What's there? It says microwaves are reflected off the oven wall. The reflected waves superpose and interfere. Then you get maximum destruction, maximum. Yeah, so I think that the kind of the word bingo that you want to have is you want to talk about reflected waves. They need to be coherent. They're going to superpose, or you could say interfere, and then you're going to get constructive, or when you get the maximum constructive interference, this leads to the antinodes. So these are the kind of words that you want to get into your lovely sentences, and then you're going to get your maximum destructive interference. And that's where you have nodes. Okay, and you might say that, yeah, that's kind of stuff that you need. Basically, these are the kind of words you want to get in your answer describing how that's formed. It says the distance between two successive points where the chocolate has melted is 6 centimetres. Determine the frequency of the microwaves used by the oven. So I'm just going to use the wave speed equation that says V is equal to F lambda, and therefore F is equal to V over lambda. Now, if it's a microwave, we'll assume that it's travelling at the speed of light, the speed of electromagnetic waves, so 3.00 times 10 to the 8. Now the wavelength, well, it's going to be 6 centimetres from an antinode to another antinode. And an antinode to an antinode is equal to half the wavelength. If you think about what's going on inside that microwave, then we're going to get basically, here we go, is that right? Okay, we're going to get, yeah, basically this is an antinode, an antinode, an antinode, an antinode, and the distance from an antinode to an antinode is equal to half the wavelength. So if we think about a wave, it would go from the top down, back up again. So that means if it's 6 centimetres from here to here, that means the wavelength is going to be equal to 12 centimetres. Is that right? And therefore, the wavelength is 0.12. So this gives me lots and lots of stuff. Therefore, the frequency is 2.5 times 10 to the 9 hertz, which I think looks right. Why does the chocolate only melt at the position shown in the diagram? That is where the antinodes are, and therefore you're going to have the strongest or the highest amplitude signal. Is this working at the moment? Is this all good? The strongest microwave amplitude. Okay, it's all good, right. What is an actinode? Sorry, that's an N there, so it's an antinode is what it's supposed to say. Sorry, that should say antinode. Explain the purpose of the rotating turntable in the microwave. You'll actually notice, well, first of all, everybody's already gone to air cookers or air fryers, so people aren't using microwaves as much. And actually what you might have seen is that modern microwaves don't always have a turntable. They just somehow control by magic the way that the signal, the waves don't have like certain hotspots. But the idea of the rotating turntable is that it rotates where the food is, so that the food doesn't just stay at one position, it moves through antinodes and nodes, so you get even cooking. Okay. Yeah, basically, explain purpose, so food cooks evenly. Basically, that's the purpose, because of what I explained. Right, here we go. There's a bit of a mess on my floor with lots and lots of bits of paper. How's everybody doing? Is everybody quite confident for their paper 2 exams, which are, by the way, you've got like a week until your exam, so you've got plenty of time over the next week to do lots of revision, to catch up. A lot of people asking about what can you do for the last week? Well, it's basically what you've already been doing for paper 1. That means as many past papers as possible. You can have a look at other past papers in addition to the ones from your own spec. So this could be looking at other examples, but maybe just picking out individual questions rather than the whole paper. You might want to have a look at some of the AS level papers. So this isn't so relevant if you're doing AQA paper 2, but if you're going to be doing OCR, exploring physics, for the people who this kind of video is really aimed at tonight, you'll realise there's lots of questions about waves and things like that in the kind of year 12 topics. So don't forget you can have a look at the AS papers for lots of topics which could come up potentially in the exploring physics thing as well. Okay, the Lego Power Pack. Shall I get that? Okay, just a bit of a brief interlude. I've got a couple of things here. This is my Lego Power Pack, which I'm particularly pleased about. You can see it's even got like the kind of cooling bits and the plug on the back. So that's my Lego Power Pack. I'll just put it there at the back. And the other thing I've got is this one over here as well, which I don't think anybody's ever made before. This is kind of like an ammeter. So you've got like the kind of the unit here that you can plug things in. I've got the kind of, I tried to sort of colour match it to be like the old kind of science equipment. And then I've also got the kind of the brown bit, the shunt at the front, where you'd maybe put in the wires, and this can then make it into an ammeter or a voltmeter potentially. So yeah, I've got these. I was actually thinking about, could I make like a massive oscilloscope in like a kind of a, I borrowed an old broken power oscilloscope from when I was teaching like the other week. They were going to throw it away, and I'm thinking, could I make one of those in Lego? But I've looked at the cost, and I reckon it'd be about £250 to make it, which I don't know if is a massive waste of money. Yeah. So he's made a Lego Geiger counter. Yeah, that's pretty cool. Yeah, maybe I need to make one of those. Right, I'll just put it over there. So yeah, I'll show you the oscilloscope. So I was thinking, could I make one of these in Lego as well? Now this one here, it's kind of quite big compared to the other items, but I was thinking, could I make this in Lego and like have like a mobile phone screen that kind of plays a video that looks like the oscilloscope screen? So, and also I could probably do it in Lego in this kind of horrible old brown colour, but I reckon I could do that. But it's just trying to think, is that a good use of money? Anyway, yeah, basically, in order to let me do that, please come along to my masterclasses. You can see I've got a link down here. The more people in my masterclass means the more money I can generate to actually buy the Lego to make these silly things. There you go. Right. Right. Did I make it myself? Yeah, I made these myself. Just, they took longer than I thought, and they cost more than I thought they would. Right. Let's go back to doing some proper physics then. So, the table below shows the results of an experiment to investigate how the de Broglie wavelength differs with its velocity. So, I would say if you got something like this, I'd just write down that this is kind of what we're expecting, that the wavelength is equal to Planck's constant divided by the momentum. Yeah. Right. Use the data in the table to show that the de Broglie wavelength is inversely proportional to the velocity of the electron. So we need to show that V is proportional to 1 over lambda, or vice versa, and therefore V lambda should be equal to a constant value. So what I'm going to do here is just another column for myself, which is going to be V lambda. Now they're all 10 to the 7, they're all 10 to the minus 11. So if I just multiply the numbers together, that's 7.35, 7.25, and 7.35. So I would say that this times that is going to be the same, and therefore I guess we can say that V times lambda is approximately equal to 7.3. Therefore it's going to be a constant value, and therefore the wavelength is proportional to 1 over V. So what I would be doing is kind of doing the calculation, making it really clear, and then writing a nice sentence that kind of sums this up. So we can use the data to then kind of verify this relationship. Determine a value for Planck's constant from this data and give an appropriate unit. So we know from the equation for Planck's constant, or from the de Broglie wavelength, that lambda is equal to h over mv, and therefore the Planck's constant is equal to lambda v times m. Now we've just worked out the wavelength times v, and I'm going to use a value of 7.3. So that's equal then to 7.3, and this is times 10 to the 7 times 10 to the minus 11, which is really 10 to the minus 4. We're going to multiply that by the mass of an electron. Yeah, because it's an electron in the question, and therefore that mass is going to be 9.11 times 10 to the minus 31 So this gives me an answer equal to 6.65 times 10 to the minus 34. So I'm going to say that's about 6.7 times 10 to the minus 34. The units, if you can't remember them, it's going to give it to you in your data book. So here, that's joule seconds. There we go. I always forget what that is. Okay, I'm going to be going through the entire paper, UNC. Yeah. Right. So yeah, basically that's the answer that we're expecting about, yes, something in the order of 10 to the minus 34 joule seconds. Yes, the live stream will be available afterwards. So if there's anything you want to kind of catch up on from the multiple choice, or you want to watch again, then you can do that as you see fit. This has to be, yeah, that's not the best diagram in my opinion. I know what it's showing, but it's maybe not as clear as it could be. State the property of graphite that allows this pattern to form when you've got electrons incident on a thin piece of graphite. So what we have here is electron diffraction. So the property of graphite is that it acts like a diffraction grating. And it acts like a diffraction grating because we've got a regular lattice, because there's a regular lattice structure, and the spacing of the atoms is going to be similar to the wavelength of the electrons which are moving through it, and therefore it acts like a diffraction grating, and that's why we get effectively like it's like a two-dimensional kind of diffraction grating, which is why we see this pattern. Okay. Explain how the pattern produced on the screen demonstrates that electrons are behaving as waves rather than particles. Basically, waves must diffract. Electrons must diffract and interfere to produce a pattern. And of course, I'm not going to write out the whole answer here, but basically the only way that we can have these dark and light fringes on that screen is if the electrons are travelling like waves, which means as they go through that lattice, they get diffracted by the lattice, and this is because they've got wave-like properties. They've got a de Broglie wavelength as they're moving at a certain speed. And after they've diffracted, there's then this interference. We have constructive and destructive interference of the electron wave until it hits the screen. I found these questions, by the way, on PMT Education. They're free to get. They email them out to you, and I'm just using them because they're a good source of like copyright-free questions. Okay, so electrons must diffract and interfere to produce the pattern, and therefore we've got wave-like properties. And this is wave-like properties as they travel. Okay, the next part of the question says, the fluorescent screen emits light. How does this phenomena demonstrate electrons behaving as particles? So just think about the electrons within that kind of phosphor coating. If you've got an electron down here, it can be energized and move up to a higher energy level. And it does that when you've got an electron that's coming in, and that then gives this electron some energy. So you've got the interaction of an electron interacting with one other electron, and therefore we've got this particle-like behaviour. And then as the electron goes back down in energy level, it then emits a photon at a certain frequency. Okay, so then we've got this kind of particle-like nature of things. So, by the way, there's lots of stuff here. This is a 2 hour 15-minute paper, and it's not extra time. This is just a 2 hour 15 paper, but the OCR people have a lovely paper 3 that's only, I think, an hour and a half long. Is that right? Whereas AQA, you've got, again, like a big old 2 hour paper at the end of the course. Okay, so what you can talk about here is that you've got an electron interacts as a particle with one electron, and then that electron in the phosphor coating goes up an energy level, and as it de-excites, it emits a photon of radiation of a certain frequency. So I guess that's how that phenomena shows that we've got electrons behaving as particles. Okay, right. Okay, so we've got a question about a capacitor. We've got it's charged to 6 volts, discharged through a 100 kilo ohm resistor. Sketch a suitable circuit for how they could investigate the voltage across a capacitor when it's charging or discharging. So we need some kind of power supply. We have this lovely kind of switch. Here we've got, right, always draw your diagrams in pencil. I'm going to start again. Right, so this is a capacitor charging discharging thing. We've got a power supply that's going to charge up our capacitor. And then of course what we can do is we can flick the switch to the other position, and then we send that through a resistor as it discharges. But we want to look at how the voltage across the capacitor changes, and therefore we need to have some kind of sensor across that capacitor. Now normally we might use a voltmeter, but we can also use an oscilloscope, which they've given us the symbol for over here. They've given it to us like that. So basically this is my oscilloscope set up across the capacitor, so we can look at the capacitance as it's charging up, if the switch is in this position, or we can flick the switch and then it can discharge through that. Okay, right. Here we go. An oscilloscope has the following Y gain, that's that one, and time base. So this is basically the Y-axis, that's the X-axis, and we've got this kind of discharging, charging, discharging thing. Determine the time constant of the discharging circuit, and hence the capacitance of the capacitor. So, 4 marks available. So we want to know CR, the time constant. Now there's an equation for that basically says, what's it say? The time constant is RC. This is the time it takes right, somebody says, are you talking about me? Are you the southwest? The guy single-handedly saved my paper one. There's a fire next to your exam hall, and you kept running through my videos while you're waiting for the fire brigade. Really? Is that true? I don't know. That's awesome. Yeah, hopefully that didn't put people off too much, and I guess the exam started okay. But yeah, there we go. Thank you. Right, I'm the GOAT. Thank you, Miles. It's been said before. Never got an award though, ever. So not even a physics teaching award from the IOP. But there we go. What can you do? Okay. So the time constant. What is the way that you can work this out? Well, basically, let's look at the graph. We've got something which discharges, and it says here that on this axis here, one of these is 1 volt. So effectively, that's 0 down here, and we can look at the initial potential difference. Is this value up here, which is about 6 point, it's hard to see, maybe 6.3 volts. Okay. Wow, that's cool. No way, you had a 45-minute X. My head's so shiny. Thank you, UNC. It's because I've got loads of lights on top of me, and it's the summer. Oh, I need to wear a cap now. I'm going to be all in, like. I need to. If I turn all the lights off. Here we go. Right, is that better? So there you go. Lights are off, but I guess you can't see anything. But my head. Does it still look a bit shiny? Maybe it does. Right, I'll turn the lights back on. So. Yeah, it's the aura, right. Okay, so we go from 6.3 volts, and then we're going to drop down over a certain time. But of course, we can actually look at the time on here. Effectively, that time there is 0. So let's say this is kind of the time of 0 when things start acting. So we've basically got a VT graph. So we've got a graph here that's basically potential difference against time, and it looks a bit like this. So what would be the equation that we can use by looking at the data on the graph to actually work out the time constant? Well, the time constant is going to be the time it takes for the capacitor to discharge to 0.37 of its original value, okay, or 0.69 RC. Yeah, so we could look at, there's two ways of doing this. Let's see, so, sorry, ln 2 equals, so somebody's saying 0.69 RC, right? Miles, it could be. But what I'm going to say is it's gonna 0.69 RC is the time it takes to fall to half the original amount. So let's say that it went from 6.3 down to 3 and a bit. So that's going to be here. I think that looks to be about 0.4. It's about 0.4 of one of these, which is 0.4 times 0.5, which is 0.2 seconds. I think it's a bit difficult to actually read it off the scale here. Let's see what it says here. Well, the mark scheme says something in the range of 0.2 to 0.35. Yeah, so basically this is the time it takes to drop to half of its original value is going to be equal to 0.69, which is the natural log of 2. So the time to go to half the original value is going to be ln 2 times CR. Okay, I think it's quite difficult to actually read the scale here, but I reckon that's 0.4 of a square multiplied by the reading on the time division, which is 0.5 milliseconds. So that would be equal to 0.2 milliseconds. So yeah, I think the time constant is about 0.2 milliseconds. Yeah, the capacitance then, well, if the time constant is equal to CR, and we know R, then R is 100 kiloohms, and we were given that in the first part of the question, and therefore the capacitance is equal to the time constant divided by R, which is 0.2 times 10 to the minus 3 divided by 100 times 10 to the 3. So that's 2 times 10 to the minus 9. What's that look like? I think that's about right, looking at what they've got. They've got something in the order of 10 to the minus 9. Okay, yeah, on the mark scheme it says 0.35. But I can't... It does also say on the mark scheme in the range of 0.2 to 0.35. So I would say, yeah, I think it's about right. I think that's right. If it's wrong, I'll come back to it later. I think that's okay. Yeah, right. It is suggested change the time base setting to 0.2 milliseconds per division could reduce the uncertainty. State and explain using calculation the advantage of this adjustment if it were to be made. So effectively, rather than having the data doing this, if this was where you had 0.5 milliseconds per division, if you made it 0.2 milliseconds per division, we then have something that looks like this. If you had 0.2 milliseconds per division, because what it would be doing, it would be stretching out everything on the x-axis, and that means that it would be 0.5 over 0.2, which is 2.5 times bigger, I guess, and therefore we'd have 2.5 times more spread out, and therefore you'd reduce percentage uncertainty in reading by 2.5 times. I think that's what it's after. Yeah, so the calculation would be you'd have 2.5 times less uncertainty if you spread the data out 2.5 times along. How are you staying motivated to revise? Good question. Often I think it's just a bit of fear and panic. Yeah. Right, the capacitor has two parallel plates with a dielectric that consists of polar molecules between them. So here is a standard air gap in your capacitor. What we can do instead though is we can put in a dielectric in the middle. Okay, so here's a dielectric. So imagine that was positive originally and that was negative. That's still going to be positive and that's negative, but that means that the polar molecules in the dielectric, they're going to line up with this to make this side negative and this side positive, I think. Is that right? So you're going to have like the kind of polar molecules lining up like that. And of course, the capacitance, is this right? Okay, let's have a look. So capacitance is equal to Q over V. Now Q is going to be the same, but what this does is it reduces V and therefore C increases. Okay, so what we're doing is we're reducing that potential difference, but what that means then for the same charge, and therefore we have a greater capacitance on this capacitor. What's the mark scheme say? It says, actually it says what the mark scheme says. It says the electric field between the plates causes the polar molecules of the dielectric to align with the field. This produces a counter-electric field, or it reduces the electric field strength between the plates, and this reduces the PD across the plates, and since the charge on the plates remains constant, the capacitance will increase as C is equal to Q over V. There we go. I will be doing the AQA predicted paper tomorrow evening. That is my evening sorted for tomorrow from about 7 o'clock when I'll do the AQA predicted paper. Yeah, so basically in your answer you want to kind of, and I think drawing a diagram could help and including an equation could help, and then you need to write 2 or 3 good bullet points explaining what's actually happening. Okay, define the binding energy of a nucleus. This is basically the energy required to separate all the nucleons into their individual I'm going to say the energy required to separate all the particles in the nucleus, actually. Particles in the nucleus into their individual nucleons would be my kind of wording for that. Somebody has got 7 exams in the next 2 weeks. Yeah, I think everybody's got a pretty intense time. I think it started off fairly slow before the half term. You then had a whole week off, which is kind of needed. And I think now for a lot of people it's just exam, 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 exam. But it will soon be over as well. Do I teach in a school? I did do some teaching for the last couple of weeks actually. So between Easter and half term, I was teaching some year 13 class, who, by the way, I don't know if they told you, but I'm not going to be there this Thursday or this Friday. If you're watching this and you're one of my students, I won't be there from now onwards. But yeah. Right, naturally occurring uranium consists of predominantly uranium-238 and a small amount of 235. In nuclear reactors, the fuel consists of enriched uranium. What is meant by enriched? So basically, if it's enriched, this means we have more uranium-235 because uranium-235 is a fissile type of isotope. Okay, so explain what is meant by enriched uranium. So basically, enriched uranium with a greater proportion of uranium-235, which is the fissile isotope, and that means so it has a greater chance of, I can never spell the word absorbing. Is it a B or a P? It's absorption with a P, so I think it's absorbing a thermal neutron and fissioning. Yeah, I think that's probably not best grammar, is it? Somebody was too locked into the walkthrough and they got ketchup on their laptop. These things happen, don't they? Yeah, these things happen. I think I looked at my laptop the other day and it was filthy. You know when you just use it all the time, you just close it and then you open it and you use it. And I looked at the state of my laptop, it was disgusting. But there we go, these things happen. Right, so uranium with a greater proportion of uranium-235, which is the fissile isotope, and that means there's a greater chance of absorbing a thermal neutron and then fissioning. Okay, does uranium-238 or 235 decay? Normally, it's uranium-238 will decay and give out radioactive radiation, and I think it's an alpha emitter, but I can't remember. But uranium-235 is the one that it doesn't so much decay, but it can capture an extra neutron and then fission apart. Okay, occasionally I think you get spontaneous fission of uranium-238, which it can spontaneously just break into two things. But it's mainly uranium-235 where we have induced nuclear fission, which is when it has to absorb an extra nucleon to become an extra neutron to become 236, and then that then fissions apart. Complete the equation below for the induced fission. So induced fission means that we've got this neutron coming into it. The numbers on the bottom, that and that, do equal that. The numbers on the top have to equal 200. Well, okay, so there's the numbers on the top are 236 on the left hand side. We're going to take away 98, and then we're going to take away, because there are 3 of these, we're going to take away 3, leaving 135. So it's 135.54 for xenon. That's right. Yeah, cool. Okay. Fissile. Yeah, fissile means it's oblivion. Fissile means that it will undergo nuclear fission and split apart. Okay, right. Right, to induce fission, it absorbs a thermal neutron. Describe what is meant by a thermal neutron. I guess this is one that is slow moving, and therefore it's got just about the right amount of energy that it can be absorbed by that nucleus. A slow moving neutron. That's what it says in the mark scheme. This is good. I've not really had enough time to prepare, to be honest. I haven't actually seen the mark scheme to actually see what the answer should be. Right, this shows a graph of the binding energy per nucleon in mega electron volts against nucleon number. Mark on the graph above the position of each of the 3 nuclei from the nuclear fission equation in part C. Okay, so let's have a look. I'm going to do this in pencil because that's what you should be doing. So we've got some stuff here. So we've got uranium 23592. So uranium is 235. So if that's 23240, it's going to be here in the middle. That's probably a bit difficult to see, so I'm just going to put a dot where I did that. That's probably difficult to see as well, isn't it? Okay, we've then got xenon 135, so that's 131. So xenon is up here in that point, which I'd probably do with a nice large cross for the exam. And then we've got, that's strontium, is it? SR? Does anybody do chemistry? It's SR strontium. I can't remember what it is. Are there any other moderators apart from water? I think boron can be used as a moderator as well, and I think boron could be one of them. Right, the next one then is strontium 98, so if that's 100, 98 is going to be about here, so it's kind of there, isn't it? Right, so that's the SRXE uranium. There we go. So those things there, that should probably, was that 1 mark, is it? Oh, 2 marks, okay. The next question, based on figure 21.1, determine the energy released in the fission process. So, this is actually looking like quite a nice question. So the uranium, the number, so I'm just going to write this to the side. We've got SR, Xe, and uranium. So the binding energy per nucleon of the strontium is about, well, if that's 8, it's about 9.6, no, 8.6. The xenon is about 8.4 megaelectron volts per nucleon, and the uranium is about 7.5, something like that. And again, if you had to do this in the real exam, they'd make this graph nice and big so it's easy to actually take the data that's needed. Okay, so the question says, determine the energy released in the fission process. Now, what we can look at then is the total binding energy of the xenon, the total binding energy of the strontium, and look at the difference between that and the binding energy of the uranium. And of course, there's going to be no binding energy for the neutrons because there's nothing they're bound to, they're just individual things. So, to do this question then, we can look at the initial energy, which was 235 times the energy for each thing in the uranium, which is 7.5. And then we can then take away the energy afterwards, which was, in the strontium we had 98 things, each of which had an energy of 8.6, and then we're going to take away the xenon, 135 things, each of which had an energy of 8.4. Okay, so let me just work this out. So this is a change in energy equal to 214.3 megaelectron volts. So the energy released would be, I'd say 210 megaelectron volts. I'm going to say this because I reckon, looking at my plotting of the graph and reading off data, I can probably get most of this to about 2 significant figures. So I'm going to give my final answer to 2 significant figures, which is actually what they've got as well. They've got 214. So I would say that justifiably I could give this to 2 significant figures. So I thought that was a nice approach. If you can plot stuff on this graph, then you can look at the energy per nucleon for these different things. Right, is that making sense, everybody? How are we doing? It's, what time is it? It's 9:15. Has anybody been here from the start? Have I just been on in the background while you're eating your tea, spilling stuff on your laptop and whatever? Okay, use your answer from F to estimate the energy released when a kilogram of uranium containing 5 grams by mass of uranium-235 undergoes fission. Okay, somebody's been here, UNC. You've been here from the start. I've seen your name several times. Yeah, that's awesome. Right, so basically, that is the energy when... So basically, we're going to release 210 megaelectron volts when 1 uranium fissions apart. Okay, so my thing would be, if you've got a kilogram of uranium, which is 5% by mass, then that means you've got 50 or 0.050 kilograms of uranium-235. Okay, So we want to know how many particles are in it, and the number of moles is going to be the mass over the molar mass. So the number of moles is going to be equal to the mass over the molar mass, which would be 0.050 over 235. Is that right? Do I need to convert one of these into grams? So that's equal to 2.12 times 10 to the minus 4. Somebody, Ahmed, says that you're stressed about the fact that you haven't started revising. Just start. Just don't keep putting it off. Just have a go. Just do an hour of revision tonight, and you'll feel so much better that you've actually made a start. The hardest thing is starting. Once you've started, it's actually okay, but the hardest thing is starting. So just do it either tonight or tomorrow morning. Get up an hour earlier. Just do an hour of revision before you'd normally be up, and then just see how you get on from there. Oh yeah, 235 is grams per mole. So in that case, I'm going to do the top one in grams. So I'm going to do 50 divided by that. So 50 grams over 235 grams per mole, and therefore that's equal to 0.2127 moles. So the number of particles is going to be the number of moles times Avogadro's number. So 0.2127 times 6. I should know this off the top of my head. 6.02 times 10 to the 23, which is 1.28 times 10 to the 23 uranium atoms. Okay, so that's good. Now we've got that much energy for each one and that many particles. So if we multiply the number of particles by the energy released in each one, and then we're going to convert from mega electron volts into joules. So we're going to multiply by 1.60 times 10 to the minus 19 to go from electron volts into joules, and then times that by 10 to the 6 to go from that thing into mega electron volts. So I think that's the right thing. I've got 4.3 times 10 to the 12. Have I made a mistake there? Right, let me see if this is the right answer. Yes, it is. Woo! They got 4.4 because they didn't round down, but this is about 4.3 times 10 to the 12 joules. So that is a huge amount of energy from just 1 kilogram. I think that's what this was trying to do. So basically I've got 10 to the minus 19 times 10 to the 6, which I then wrote as 10 to the minus 13 on my calculator, which is just 10 to the minus 16 times 10 to the 6, that's 10 to the minus 13. That is a lot of energy, but that's because you get a lot of energy from a small amount of fuel. Right. Oh my gosh, have I not finished yet? Oh, this is going on and on and on. Right. How many more questions? Have we just got one more question? Oh, that's good. Okay, we've just got one more question, people. The Lego isn't official. The Lego behind me, are you talking about? Yeah, that Lego behind me there, that the kind of scientific stuff isn't official, but maybe I just need to start building more stuff. Right, I think we've only got one more question, haven't we? You're doing well, people, if you're hanging in there. This one here. The definition for Lenz's law. This came up and I talked about it in my masterclass, which I did on Saturday morning. By the way, OCR people, I am doing another OCR masterclass this Saturday morning from 10 till 12. If you haven't already done so, make sure you sign up. It's only £30 for 2 hours of me doing lots of glorious physics stuff. But we looked at Lenz's law. And here is what it said in a real exam. And OCR said the direction of the electric current induced by a changing magnetic field is such that the magnetic field created by the induced current opposes changes in the initial magnetic field. So this thing here, it's a long, wordy sentence. Take a picture of this now, do a screenshot, get your phone out to take a picture of your laptop. This is the best definition I've seen of Lenz's law because it has been written by OCR themselves. So this has obviously been sanctioned and approved at the highest level within the OCR community as a good definition, even though it's very, very wordy, of what Lenz's law is. It's about how the direction of the induced electric current caused by a change in magnetic field is such that the magnetic field created by the induced current opposes the changes in the initial magnetic field. There we go. That would be my statement I would write down. Get it memorised, put it on a flashcard, come back and look at this live stream later so you've got the definition of it there, which is what you've got. Yeah, don't forget it. Just keep it in your mind for the next week. In a week's time, you never need to know Lenz's law again. Right, 2 small solid metal spheres are made of aluminium. So a question like this, there's a lot of information. So I'm going to draw a diagram. There we go. They have the same radius, but Y has a greater mass. So 2 solid spheres, X and Y. So this is X and this is Y. They're made... that's not true. They have the same radius, but Y has a greater... Okay, X and Y. So we've got aluminium and we've got steel. So I'm just going to put Fe for steel. They have the same radius, but Y has a greater mass. Okay, what material property accounts for this difference? I guess it would be density. Because density is mass times volume. If they've got the same volume but a different mass, that must mean they've got a different density. Okay, right. Show that when both spheres are dropped from a height of 1 metre that the time it takes to land is 0.45, and explain why the time to land for both spheres is the same. So if I think about one sphere, the force acting on it is its weight, which equals mg. Okay, so this is going to be the weight force acting down, but that weight force down, W, is going to be the resultant force on it. So basically, we know that the force is equal to mass times acceleration from Newton's second law. So that's Newton's second law over there. Force equals mass times acceleration. The thing that provides the resultant force in this case is the attraction of the Earth, and therefore that resultant force is equal to mg, which is equal to ma. The m's cancel, and therefore the acceleration is caused by the gravitational field strength. Okay, so basically this means that acceleration independent of mass, and this is provided there's no air resistance. So that's basically the second part of the question. Okay, right. The next thing then is to actually look at the time. So I'm just going to write down so that we know the height it falls is 1 metre, the initial velocity is 0, the acceleration is 9.81, which is what we worked out up here, and we want to know the time, and therefore time we can use S equals v squared. No, we don't need, we want something without v in it, so we can say that S is equal to ut plus a half at squared. So we can rearrange this to say that t is equal to 2s over a square rooted, all good standard stuff. Right, which is equal to 2 times 1.0 divided by 9.81 square rooted equals 0.45. Okay, so that question, a bit of a weird one, but basically we use the CVAT equation for something falling, and the reason that it doesn't depend on the mass is because the resultant force that causes it to accelerate is equal to its weight, which is mg. So mg causes this mass to accelerate, the m's cancel, and therefore the acceleration is g, and that means the acceleration is independent of mass. Cool, right. Oh god, is this the last question? Oh, it keeps going on and on. Right, okay. D. The steel sphere is a strong permanent magnet. Okay, both spheres are allowed to fall through a long hollow vertical tube. Okay, so basically we've got a long tube like this, and we drop the spheres through them. Now the one which is made out of steel takes a lot longer than the one which is made out of aluminium. Why is an EMF induced in the copper tube as Y passes through it, and why does it take longer? So basically you're just going to describe Lenz's law again. So what you have is, and this is where I'm not going to write it all down now because I can't be bothered, is we've got a moving magnet, and this moving magnet is near to a conductor. Now, if you've got a movement, this changing flux, induces an EMF. And of course, if you've now got a complete circuit, which is what you do when you've got this flows in the copper. And of course, if you've now got moving charges, we then have an associated magnetic field. So the current flows in the copper, causing this opposes the change that caused it. So we've now got a magnetic field caused by the steel. So we've got a magnetic field moving down that induces an EMF, which therefore induces a current. And if you've got a current, we've got an associated magnetic falling magnet down. And if it's slowing it down, it's going to spend longer in the tube. So this is a great example of Lenz's law. Okay, right. The copper tube is replaced by a brass tube with the same dimensions. Brass has a much greater resistivity, equal to Ra over L. So if it's got the same dimensions, then if it's got a greater resistivity, it's going to have a greater resistance. With a greater resistance, because R is equal to V over I, if you've got a greater resistance, for the same potential difference, we'd have a lower current. So that means as the magnet is falling, it would induce the same EMF, but that would cause a lower current to be flowing. Okay, hopefully you can see that. So describe the effect that it takes for X and Y to pass through the brass tube. So time for X is no change. So there'd be no change as the aluminium ball dropped, because there wouldn't be a magnetic field causing these kind of currents with Lenz's law. But if the time for Y the time would get quicker, so the time would reduce as the force against it. Oh, hi Zed, physics, hello. Just coming right in at the end, yes. Have you been doing a class today, have you? Right, yeah, so Zed Physics. By the way, for anybody watching, if you haven't already seen, Zed Physics put up a massive video where we worked through, or basically he worked through a whole Olympiad problem. I would say probably by this point it's a bit too late to kind of get to grips with it. Great for anybody in year 12 looking at how work on gravitational fields is really important for like kind of DART missions and sort of stuff in space. But yeah, basically, if you want to go and have a look at there we go, Zed Physics has just come back from the climbing wall. Basically, if you want to have a look at this Olympiad problem, have a look at Zed Physics' channel and his latest video that he put up on Sunday. Also, Zelia, I went up Crib Goch, so I was up in Wales on the weekend. Last week, midweek, I did a quick, just one night trip over to North Wales. So not quite the kind of climbing that you're doing, but I did a bit of scrambling, which still felt quite terrifying in the rain at the time. But yeah, we need to go and do some mountaineering at some point. Right, back to the question. So the time for Y, it will reduce as the greater resistivity causes a lower current. And I guess you could then kind of really write to say that if you've got a lower current, we then have less of a force acting against the falling magnet, and therefore there'd be less braking effect. All right, I think that's it. I'm done. There's so much like paper on the floor. I think I got most of the questions correct. I think the only one I'm not sure about is the one I did with the capacitor. So I'll kind of put a correction underneath if I did that incorrect, but I think I got the right answer. Basically, that was the end of the OCR predicted papers. It's not predicted, it's a good set of questions, which are the style of exam questions that could come up, and therefore it's a good thing to do as part of your revision. But if you haven't already done so, make sure that you do at least all of the other 8 exploring physics papers for OCR, going from 2024 back to I think 2017. I've got a masterclass later this week coming up on Saturday morning, so you're more than welcome to come to that. You can just sign up on my website. It's only £30, but I do have limited spaces, and I know there's thousands of people probably going to be watching this video. So does somebody want me to do a vlog? To be honest, a day in the life vlog of me isn't super interesting. It's just like me sat at my laptop or sat at my computer just making resources and editing videos. But I'll do some more vlogs at some point. I guess me and other physics teachers do have a life outside of teaching, so maybe I need to do the kind of physics diaries. Anyway, I think that's going to be pretty much it for tonight. So if you haven't already done so, make sure you do subscribe. It would be good to get to 200,000 subscribers before the end of this exam season. And I'll see all of you in future live streams. I'll be doing an AQA one tomorrow, but again, a lot of the questions are going to be quite similar. So thank you everybody, and good night.